The story of 3I/Atlas did not begin 3 minutes ago. In fact, it did not even begin on the day the world first heard its name. The real story started 10 days earlier, at a time when no one on Earth had the slightest idea that an ancient traveler from another star system was quietly passing through our cosmic neighborhood. By the end of this journey, the reason two of the most powerful telescopes ever built, the James Webb Space Telescope and the Vera C. Rubin Observatory, both ended up studying the exact same object without anyone planning it, will become perfectly clear. But before we continue uncovering this remarkable story, take a moment to subscribe to the channel and help us reach our goal of 1,000 subscribers. Your support makes videos like this possible, and it helps us continue bringing you carefully researched stories about the greatest discoveries in science and space. On July 1st, 2025, astronomers operating the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, noticed something unusual moving across the sky from its observing station in Rio Hurtado, Chile. At first, the mysterious visitor seemed ordinary enough to receive nothing more than a technical designation, C/2025 N1. But as scientists carefully calculated its path, the truth slowly emerged. This object had not come from anywhere inside our own solar system. It had traveled across interstellar space, making it only the third confirmed interstellar object ever observed by humanity. The visitor was officially named 3I/Atlas, and almost overnight, observatories around the world shifted their attention toward it. Every available telescope wanted a closer look at this incredibly rare traveler from another part of the galaxy. Yet the most fascinating chapter of the story had already happened without anyone realizing it. Several weeks after the official announcement, researchers working with the newly completed Vera C. Rubin Observatory decided to perform what seemed like a routine task. They began searching through archived images collected during the observatory's science validation phase, a period when engineers and astronomers were simply testing the telescope rather than conducting real scientific observations. As they examined photographs taken on June 21st, 2025, they made a remarkable discovery. There, hidden quietly in the background of ordinary calibration images, sat 3I/Atlas. The object had been photographed a full 10 days before Atlas officially announced its discovery. Nobody at the Rubin Observatory had noticed it at the time. The telescope had never been searching for an interstellar visitor. That evening, its enormous camera had simply been performing routine calibration tests. Pure coincidence had pointed the observatory toward the exact region of space where this ancient traveler happened to be passing. The accidental observations did not stop there. Between June 21st and July 20th, 2025, Rubin continued capturing images of the object without realizing its importance, collecting nearly 100 exposures altogether. Eventually, researchers selected 49 of those images for detailed scientific analysis. Those accidental photographs became some of the earliest and highest resolution images of 3I/Atlas ever captured anywhere on Earth. Long before most scientists even knew the object existed, Rubin had already preserved an extraordinary visual record of its journey. When researchers carefully examined the images, they discovered that the comet was surrounded by a growing coma, a cloud of gas and dust enveloping its icy nucleus. As the object moved closer to the Sun, the coma expanded by more than 50% during the observation period, exactly as scientists would expect from an active comet warming under increasing sunlight. Everything appeared perfectly normal. Almost. One feature immediately stood out. Instead of pointing away from the Sun, as comet tails almost always do, the dust tail appeared to point toward it. That was unusual, Normally, sunlight pushes tiny dust particles away from the sun, naturally creating tails that stream outward. A sunward-facing dust tail is rare, although it has been observed before in a small number of distant comets. Fortunately, astronomers already had a scientific explanation. The effect can occur through a process known as anisotropic dust emission, where dust is released unevenly from different regions of the comet's surface. Depending on the viewing angle, that uneven release can create the appearance of a tail pointing toward the sun. It was certainly an interesting feature, but not an unexplained mystery. To fully appreciate why this accidental discovery mattered so much, it helps to understand the remarkable telescope responsible for capturing it. High atop Cerro Pachón in Chile stands the Vera C. Rubin Observatory, built where exceptionally dry air and some of the darkest skies on Earth provide nearly perfect conditions for observing the distant universe. At the heart of the observatory sits an enormous primary mirror measuring 8.4 meters across, roughly the length of a tennis court. Mounted behind it is the LSST camera, the largest digital camera ever constructed, capable of recording an astonishing 3,200 megapixels in a single exposure. Yet, when it photographed 3I/Atlas, the observatory had not even begun its official scientific mission. It was still participating in science validation, essentially a dress rehearsal during which engineers and scientists carefully tested every part of the observatory before launching its full 10-year survey of the night sky. During this science validation period, the observatory was not chasing discoveries. Instead, engineers and scientists were carefully examining every part of the system. The optics had to perform flawlessly. The massive camera had to prove it could capture razor-sharp images. The software pipelines had to process enormous amounts of data accurately. Every component was being tested long before the real 10-year survey would officially begin. Night after night, the telescope was directed toward different regions of the sky, not because astronomers expected to find anything extraordinary there, but simply to verify image quality, calibration accuracy, and the overall reliability of the observatory. Searching for specific objects was never part of the plan. That simple fact explains why nobody noticed that 3I/Atlas was quietly sitting inside those early test images. The photographs had been taken weeks before anyone even knew such an object existed, so there was no reason to search for it. Only after Atlas officially announced the discovery did researchers return to the archived commissioning data with a single question in mind. Had this mysterious visitor appeared in any of Rubin's earlier observations by pure coincidence? The answer astonished everyone. There it was, quietly hidden in ordinary calibration images, patiently waiting to be noticed. The observatory had unknowingly recorded the interstellar traveler 10 full days before the rest of the world even knew where to look. The discovery also revealed just how remarkable the Rubin Observatory truly was. Every image captured by Rubin is recorded through one of 6 different optical filters, each designed to observe a different portion of visible and near-infrared light. These filters are known simply by the letters U, G, R, I, Z, and Y. By comparing observations across all 6 bands, astronomers can measure both the position and brightness of distant objects with extraordinary precision. For 3I/Atlas, scientists determined its position with an average precision of roughly 70 milliarcseconds, an incredibly tiny angle considering both the immense distance to the object and how faint it appeared during those early observations. Even more impressive, Rubin routinely measures fixed background stars with a precision closer to only 3 milliarcseconds. The slightly lower precision for 3I/Atlas was not a limitation of the telescope itself. It simply reflected the added difficulty of tracking an object actively moving across the background of space. Those accidental observations soon became far more than interesting photographs. Led by astronomer Colin Orion Chandler and supported by more than 300 collaborating researchers, the scientific team used Rubin's early images to publish a detailed study of the comet. They carefully analyzed its astrometry, the precise measurement of its position through space, while also examining its brightness, shape, and level of activity. Every conclusion in that paper came directly from data that had been collected before anyone even knew the object existed. By then, however, another observatory was preparing to continue the story. On August 6, 2025, the James Webb Space Telescope turned one of its most sophisticated scientific instruments toward the ancient visitor. Its near-infrared spectrograph, better known as NIR-SPEC, began studying 3I/Atlas in detail. This marked Webb's first dedicated observation of the object, following earlier observations made by both the Hubble Space Telescope and NASA's SPHEREX mission. Unlike Rubin, Webb was not designed to survey enormous sections of the sky. The two observatories had completely different strengths. Rubin excelled at discovering objects by repeatedly photographing vast regions of space, recording their motion, brightness, and overall appearance. Webb, however, specialized in something far more detailed. Instead of simply taking pictures, it separated the comet's light into thousands of individual wavelengths using spectroscopy, allowing astronomers to read its chemical fingerprint. The results arrived almost immediately. Inside the expanding coma, Webb detected carbon dioxide, water, water ice, carbon monoxide, and carbonyl sulfide, a sulfur-containing molecule known for its strong odor here on Earth. Individually, none of these substances surprised scientists. They are all familiar ingredients that have been found in many comets before. One measurement, however, stood apart from everything previously observed. The proportion of carbon dioxide compared with water turned out to be the highest ever measured in any comet, whether it originated inside our own solar system or beyond it. For astronomers, that ratio carried an important message. The relative amounts of carbon dioxide and water preserved inside a comet depend heavily on the temperature and radiation conditions present when that object originally formed. Different birth environments naturally produce different chemical mixtures. Rather than suggesting anything mysterious or artificial, the unusual ratio offered valuable clues about the distant region of space where 3I/Atlas had first taken shape. Several months later, Webb returned for another look. By then, the comet had already reached perihelion, its closest approach to the Sun, on October 29, 2025. As increasing solar heat reached its ancient frozen surface, more and more of its ice rapidly transformed into gas, causing the surrounding coma to grow brighter and far more active. That made it an even better target for detailed chemical observations. On December 22, 2025, shortly after the comet made its closest approach to Earth on December 19, passing safely at approximately 168 million miles, or about 270 million kilometers, away, Webb captured another series of observations. At no point during its journey did the object pose any threat to our planet. This second investigation revealed something even more significant. Hidden within the comet's ancient ice were precise ratios of carbon and deuterium, the heavier form of hydrogen. Those chemical signatures did not resemble the compositions measured in comets that formed within our own solar system. For the first time, scientists possessed direct evidence that this extraordinary traveler had preserved the chemical conditions of a completely different region of the Milky Way, carrying within its frozen interior a record of an environment far older and far more distant than our own cosmic neighborhood. The deeper scientists looked into the comet's chemistry, the more extraordinary its story became. Using the unique chemical fingerprint preserved inside its ancient ice, researchers began working backward, tracing the object's history long before it ever entered our solar system. Molecule by molecule, ratio by ratio, the evidence slowly revealed where this traveler had most likely been born. The answer was astonishing. According to the measurements collected by the James Webb Space Telescope, 3I/Atlas most likely formed somewhere between 10 and 12 billion years ago in a cold, distant region of the young Milky Way galaxy. To appreciate just how ancient that is, consider our own home. The entire solar system, including the Sun, Earth, and every other planet orbiting around it today, is only about 4.6 billion years old. That means the frozen ice and dust locked inside this comet had already existed for billions of years before our own Sun even completed its formation. While our solar system was still nothing more than a collapsing cloud of gas and dust, 3I/Atlas had already spent unimaginable stretches of time drifting silently through interstellar space. Some researchers have even pointed out that this remarkable object is nearly as old as the universe itself, whose age is estimated at approximately 13.8 billion years. After carefully examining every measurement and verifying every conclusion, the research was formally published in the scientific journal Nature on June 22, 2026. Before publication, the study successfully passed peer review, meaning independent scientists carefully checked both the data and the conclusions to ensure the results met the highest scientific standards. As news of the discovery spread across the internet, another question quickly began circulating. Was this the mysterious alien object that so many online posts claimed it was? The scientific answer could not have been clearer. No. Astronomers have repeatedly explained why they are so confident, and their conclusions are based entirely on direct observations rather than speculation. The first piece of evidence came from the comet's behavior. As 3I/Atlas approached the Sun, it developed a growing coma, releasing gas and dust exactly as scientists have observed countless comets doing for decades. Every stage of its activity matched well-established physical models built from years of studying comets within our own solar system. The second piece of evidence came directly from Webb's chemical analysis. Inside the coma, scientists detected carbon dioxide, water, water ice, carbon monoxide, and carbonyl sulfide. None of these substances were unusual. They are all familiar ingredients that researchers have cataloged and studied in comets originating inside our own solar system. The only difference was their proportions. Those changing chemical ratios reveal information about the temperatures and environmental conditions under which the comet originally formed. They do not indicate artificial construction or engineered materials. Instead, they provide valuable clues about the distant region of space where this ancient object first came into existence. The third piece of evidence came from its motion. Throughout its journey, 3I/Atlas followed the predictable laws of gravity and orbital mechanics. Astronomers detected no mysterious deviations, no unexplained bursts of acceleration, and no sudden changes in direction beyond the small, natural adjustments produced by outgassing. The same subtle effects scientists have measured in comets for as long as they have been observing them. When every observation was considered together, the conclusion became unavoidable. The early photographs captured accidentally by the Vera C. Rubin Observatory, combined with the detailed chemical fingerprints measured by the James Webb Space Telescope, all pointed toward exactly the same answer. 3I/Atlas is a completely natural interstellar comet. It is made of ordinary ice, gas, and dust, much like the comets already familiar to astronomers inside our own solar system. The difference is not what it is made of, but where it came from and how incredibly old it is. Astronomers have stated plainly that the available evidence rules out the idea that 3I/Atlas is some kind of alien spacecraft or artificial probe. In fact, many researchers argue that presenting it that way actually diminishes the true significance of the discovery, because the real story is far more remarkable. Imagine holding a genuine piece of another region of the Milky Way in your hands. That is essentially what scientists were studying. 3I/Atlas is a real fragment of frozen material that formed in a distant part of our galaxy long before our own sun existed, and billions of years before Earth was ever created. After drifting alone through interstellar space for nearly the entire history of the universe, it happened, by extraordinary coincidence, to pass close enough to humanity's telescopes for us to examine it in remarkable detail. That brief encounter gave scientists something priceless. Not speculation, not theory, but direct physical evidence from another corner of our galaxy, preserved inside an ancient traveler that had spent billions of years carrying the history of its birthplace silently through the darkness of interstellar space. To help people understand just how extraordinary this encounter truly was, scientists have often compared it to finding a message in a bottle that has been drifting across an ocean for billions of years. Only, in this story, the ocean is not made of water. It is the entire Milky Way galaxy. And the bottle is not made of glass. It is made of ancient ice. That comparison may sound like science fiction, but it describes a very real scientific opportunity. Events like this are among the rarest natural phenomena astronomers could ever hope to witness during their entire careers. By an extraordinary coincidence, this ancient traveler happened to pass through our solar system at exactly the moment humanity possessed some of the most advanced telescopes ever built, already watching the sky and ready to study it in remarkable detail. The comet's chemistry was not simply interesting because it revealed what the object was made of. It also provided one of the strongest clues about when and where it had originally formed. The key lay in an element called deuterium. Often referred to as heavy hydrogen, deuterium is simply a slightly heavier form of an ordinary hydrogen atom. Inside ancient ice, the ratio between normal hydrogen and deuterium behaves almost like a natural clock, preserving information about the conditions that existed when that ice first formed. Those ratios change only very slowly over cosmic time and are influenced by the temperature and radiation environment inside the cold clouds of gas and dust where comets are born. By carefully measuring those tiny chemical differences with Webb's near-infrared spectrograph, researchers were able to work backward through billions of years of history. The measurements allowed them to estimate not only the age of the comet's ice, but also the type of environment in which it originally formed, a process astronomers describe as galactic chemical evolution. That process tells an even larger story. Over billions of years, the Milky Way has gradually changed its chemical composition. Generation after generation of stars has been born, lived out its life, and ended it by enriching